Okay, so I guess today is a little bit of a hybrid between a panel and a debate, because we have like two competing approaches. We have the bytecode compatible approach, the bytecode levels zkEVMs, and we have the language level zkEVMs, where you have this compilation step. And I guess the idea is to try and tease out some of the trade-offs of each approach. So I guess before we start, do you want to briefly mention your name, the company you're with, and also how many full-time equivalent engineers are working on your zkEVM? Yeah, let's go.
Does it work? Yes? Yeah, okay. So I'm Nicolas Liochon. I work at Consensys. And counting how many engineers are working on the zkEVM is an interesting exercise, because does it include the people working on the proof system itself? Does it include people working on the rollup part? And so I will simplify things. I will say 5, but I won't say if it includes everybody or not.
Hello, everyone. My name is Ye. I work at ScrollTech, and we have around like 20 engineers, but 10 of them working on the zkEVM implementation side, and 10 of them working on some GPU acceleration, sequencer, and also the infrastructure side. But worth to mention that for zkEVM circuit, we are not only the one like in this community. I think if you add up all the people from Applied ZKP team at Ethereum Foundation, there will be around like over 20 people working on this open source effort implementation. So we have a lot of Jesus, like everywhere, like building this, and like just you can check out the repo and just join this effort if you want.
Hello, I'm Jordi Baylina, technical lead at Polygon Hermez. We in Polygon Hermez, in the prover itself, just dedicated to the prover, we are 7 persons. Mm-hmm. And then in Polygon Hermez altogether, if you count even administrative things and all together, it's about 30. The engineers maybe 25 or something like that. And well, yeah, if you count Polygon, then it's a bunch. Yes.
Hi everyone, my name is Alex Gluchowski. I'm from zkSync, co-founder of zkSync. We have a pretty large engineering team of maybe 30 people, and yeah, what we're building is zkEVM based on a separate virtual machine.
Yes, so I'm Ohad Barta. I'm from Starkware. I think for our use case, it's a bit simpler to answer the question, because we have many engineers that work on Cairo, which is the language we have, but only very few engineers that are actually like from the Netherlands teams, or even not internal page of Starkware, work to adapt it to like having Transpilation from Solidity to Cairo. So. Okay, understood. So I mean, just zooming out, 2 years ago, zkEVMs were kind of, at least in my opinion, kind of moon math, a big moonshot. And here we are, we have like roughly 100 full-time engineers working on this technology. So really amazing. So I guess because we only have half an hour and there's so many of us, what I'm going to do is I'm going to mention some sort of keyword or some sort of topic. And I want you to raise your hand if you believe your approach is the winning approach. And if you... And if you raise your hand, I might grill you on specifics. Okay, so the first topic is time to market. Who will be first? Because we need scalability super soon. Time to market. Okay, I think there's kind of some agreement here, right? So we have this is where the split happens in the spectrum. Actually, the seating here is intentional. So we have the left side of the spectrum here, which is on the far extreme kind of bytecode compatibility. Here in the middle, we have both bytecode compatibility and kind of this new set of opcodes. And then here we have a completely new VM. So I guess you guys raised your hand. Then I guess the next question is, when will you guys launch, if you think you're going to launch first? I mean, we had scalability engine StarkX on production since 2020. And since middle 2021, it's based on Cairo, which is our language.
Right, so the topic at hand here is zkEVM. So I'm only interested in taking Solidity and compiling it down.
So we already have that as well. We have the warp, which is a transpiler from Solidity to Cairo. I guess definition is difficult for, like, do you only count the entirety Solidity, so being able to take any arbitrary Solidity code, or some manual more intervention is required, but we already have something that works and proved itself for like ERC20 contracts, etc.
Right. Alex?
So we have now, we have a different approach where we actually want to support full Solidity stack with Web3 API. So you can take any contract from, like almost any contract from Ethereum mainnet, deploy it to zkSync, use the same APIs, Web3, use the same tooling, the graph, Etherscan, whatever, like everything is the same. And it will just work. And the most important thing, you don't have to maintain two code bases. So with the warp approach, you would have to compile, transpile into Cairo, and then you have to maintain the Cairo version. With us, you actually do this. And we are the first we roll up to have a live testnet with this. And we're going to launch mainnet later this year.
Okay, Jordi?
Yeah, we plan to launch a testnet in the upcoming month, maybe 2-3 months. That's the plan that we have. Fully opcode compatible, so we don't have problems with compilers and so on. And then the mainnet, of course, there is a lot of new things that will need to be audited and checked. And, well, this is an important process, but I expect that in 3-4 months more. Maybe by the end of the year, it should be a mainnet running. That's the plan that we have in mind. Of course, still a lot of work developing, and always putting pressure here is hard, but it's good, a little bit pressure there. So let's see if by the end of the year we can have it.
Okay, great. The next big topic, developer experience. Which one is the winning approach? What?
Well,
all of you, okay. So I was kind of expecting this side to raise the hand and this side to not raise the hand so much, but okay, have your hand. I mean, I guess one question I have, for this side is like, what percentage of the existing tool set will be exactly reusable? I mean, Alex, you made a point to really reuse as many of the tools as possible. Is it 99%? Like, how far is it?
So if we're looking from the developer's perspective, we're aiming at 100%.
100%?
Yeah, so like 98% will work just out of box. And for the remaining 2-3%, we will have replacements, we will have adaptations. Like, for example, some hard hat plugins will have to be rewritten to work differently. But from your point of view as a developer, you just use your code. Like it will happen under the conditional compiling options that different library is going to be used. But for you, nothing will change.
Okay. And I guess, for your approach, do you expect kind of some reworking of some contracts, or will everything work out of the box?
Yeah, I think we are even more compatible than, because we are definitely bytecode level compatible, so you don't need to recompile. You just take the existing bytecode and directly prove that. And I think we are more like compatible. And even like as I mentioned, like we are even using Gas as our execution node. So even all the RPCs and all those stuff will be exactly the same. And yeah.
Right. And I guess you're targeting opcodes, but will you support every single opcode?
Yes.
Yes. Okay. And I guess one question is around like gas, because presumably metering is going to change. Like, how is that going to affect developer experience kind of across the board here?
Yeah, I can explain in our case. So we are going to fully simulate the Ethereum gas model. So from the user perspective, they will see exactly the same that Ethereum. So to maximize, the idea is that the developer have exactly the same experience that's developing on top of Ethereum, that developing on top of zkEVM. They should not see any difference, and this is the goal that we are approaching. But this is, of course, the gas model. So the resources that's consuming inside the zk circuit is not exactly the same that the ones that are using in EVM. In our case, the way we are solving this is the sequencer will choose whichever transactions wants to fit. So, and all the fees goes to them. So he can choose. So he will choose whatever is better than that. This is in one side. There is one important thing here, and is that when we are in zkEVM are fixed circuits, are circuits that are not. So you cannot extend as much as you want, and there are some, I would say, malicious or bad generated smart contracts, not useful. But imagine, for example, a loop that's doing pairing all the time. So, or it's doing a KEKAK, which is, for example, it's a very cheap opcode in the EVM, but when you implement it inside the circuit, is expensive. So what it may happen is that this transaction will not be able to be executed. What we are doing is we are taking, so because we need to prove the model, we need to prove that we cannot execute that transaction. So what we are doing is we are taking an internal accountability of the resources we are consuming, and then we have like a kind of an interruption in the processor. So we stop. We say that this transaction reaches this point that cannot be processed, but actually is processed. So it will not be processed exactly the same that would be in the EVM, but this transaction will not stop.
Okay. So you're saying that there's some transactions which are valid on Ethereum today that will not be valid on Hermez, and they'll have this special interruption saying, hey, I can prove to you that you're using too many resources.
This, and we expect that this should be not, so normal transactions should be included easily, but this should be just malicious, so explicitly generated transactions that go against, and then this will happen.
Right. And for someone else who's taking kind of a similar approach where you want to kind of keep the same gas schedule, do you agree that this will kind of create kind of two gas markets? Like there will be the traditional gas metering, and then maybe in the tip that will kind of influence, what the sequences will want to prove based on the computational load for them. Or do you think it will be seamless from a metering perspective?
I expect it to be quite seamless for quite a while, because it totally depends on the prover time. And the prover time is changing all the time. I mean, we have improvements nearly on a daily basis. So at the beginning, it will be quite invisible because anyway, it won't be stable enough to define a price. And the price will be dominated by the call data and the data availability that we're writing on the blockchain, and the prover time will be kind of hidden. And then with more and more optimizations, at a point we'll say, okay, now the prover time is well known, so we know that KEKAK, for example, is quite expensive, so we want to price it separately. But I expect it to take at least 5 years. And for 5 years, between software improvements, FPGA, GPUs, and so on, we won't care that much.
Okay. So you're saying that it would be foolish to try and like have a gas schedule because the prover times are always changing and they're going to improve dramatically over time. Exactly. Mm-hmm. And I guess I mean a question for you would be are you taking the same approach as Jordi? Are there going to be some transactions on Ethereum which won't be valid on Scroll?
Yeah, I think for our case, I think there won't be that cases because we are directly reviewing even the implementation from Ethereum, just a different state root, and that's it. And we actually plan to have some maybe proof of concept stuff for people to play with for proving a Ethereum block like with a different state root, because just generating proof for storage just costs you a lot. Yeah.
Right. And I guess another question I have is that these circuits are kind of limited in size. And maybe that goes against the fact that the gas limit on Ethereum can be increased. So how do you deal with that? Do you kind of enshrine a maximum gas limit for the blocks that you can verify?
Yeah. So basically, as I mentioned, like in my slides, so basically, a zkEVM circuit is verifying the execution trace. So we will have a fixed length of EVM execution. So like if we want to increase our our guess limit. We just need more a longer traces, or maybe 2 traces, but they are consistent in some sense, and they will just we just generate different proofs and aggregate them. So I don't think that's a very harsh limit on layer 2, especially on layer 2. We will unlock more computational intensive applications.
Right.
In our case, the limitation would say is more how long is the transaction that you can process? Because the thing is that if you have a transaction that it's a long transaction, a transaction that takes a lot of gas, at this point we are not splitting this transaction in different proof. We need to put that in a single proof. And this is the limitation. Currently, we are targeting, at this point for the first version, we are targeting about around 500K gas transactions, and then aggregating, so 500K gas blocks, which is a transaction of 500K, more or less. That's depends on the transaction it is. But this is what works. But increasing the size of polynomials, that means doing bigger proofs. We can go farther, much farther than that.
Right. So what you're saying is that right now, if a transaction consumes more than 500,000 gas, it will likely kind of not be.
It will be like one transaction.
But that should improve over time, presumably.
500, yeah, that's the initial
version,
is
right.
like the initial version. Actually, we are using a new technique. Well, I'm using a new prime field. We are choosing short prime fields. We are having very good improvements in the proof generation, and we probably will increase these polynomials. We are also doing a lot of research in the improving the proof times, and these numbers, we need to review these numbers because we probably can go much higher.
Okay. Next topic, prover performance and cost. Which one has the fastest provers?
I don't know the other.
Okay, interesting. Yeah, I was expecting this side to raise their hand. So I guess, do you want to justify, and how much faster will you be versus the other approaches?
Yeah. So we can be extremely fast because, as I mentioned, we will have a proving network. So at the front, you have some GPU, and you can join our network. We can process all those proofs in parallel, and so it's throughput of those proofs will be so if you are just amortize or all those proof generations, then you will get, I think it's so fast because, other zkRAPs are centralized, and you definitely need some latency because you have machine costs and those stuff. So that's one point. Also, our GPU, we have already built some GPU implementation for our prover, which I think is 10 times faster than state of the art. Even for BN curve, that 254-bit field within, switching to the Fry field, which is a smaller field. So I guess if we use our GPU and switch to a smaller field, we will maybe another order of magnitude. And it's I'm pretty confident that we will have the best prover.
Okay, so you're saying that with special hardware, maybe like GPUs, and by leveraging the power of distribution and decentralization, you can get really fast provers. I guess my next question would be, for a single machine, we have this reference machine, how much faster would this approach be? And I guess that's a question for Ohad and Alex.
Orders of magnitude? 2 orders of magnitude?
What?
How much faster is native bytecode versus full?
Yeah, I think that in some way it's tricky to measure because no one did the same proof system on both ways. But it just if you look on the set of constraints that are inflicted upon you the moment that you want to be EVM compatible in the bytecode, like memory model, making the costs adjustable, everything, there's a lot of value in being EVM truly compatible, but also a lot of downsides that we are able to avoid when we come up with different language.
Right. But would it be fair to say that there's also maybe some overhead in the transpilation process? So, for example, if you're working with binary, objects, and then you compile them to a VM which is, friendly to primes.
Yeah, I agree that if you say, okay, take this solidity, put it here or put it here, you wouldn't be as efficient as the native proving.
You'd be
with
slower.
Cairo.
Okay, interesting.
I think comparison is tricky, but if you just say, okay, how much the running time of the prover, I still expect the prover itself, the machine is much simpler, right? Maybe you'll need more instructions, but it's a simpler machine.
Alex, do you agree that the overhead of the the transpilation is greater than the circuit overhead, and that net you kind of have a slower system than the native system.
Not slow. It's hard to compare.
It's hard to compare, but like maybe it's not 10 times faster or 100 times faster.
So I will start with saying that we also work on hardware-based acceleration with GPUs and FPGAs both, and there will be networks for this. So, and we can also adopt different field sizes. So like, let's assume we all use the same proof system, because like eventually everyone is going to be using the most efficient proof system out there, and it's going to be based on the arithmetization of Plonk, Starks, whatever. They are very similar, so it's going to be really easy to transfer over. So like, but the basic approach. So like, if we're saying using native languages, they always will be the most efficient ones, right? So like, this is your approach with Cairo, and this is also our approach, because we have the intermediate step of zkSync bytecode is LLVM, which allows us to compile any language which has LLVM frontend. And this is the most popular compiler framework. So you can use Rust, C++, Python, Go, whatever you want, and compile it directly into a native LLVM and then use in our system. So we don't do this because for the sake of this discussion, we should only consider the EVM compatible things, like it's EVM compatibility versus EVM equivalence, right? So we assume that for the time being, there will be no ecosystem in other languages. Like it will need to be bootstrapped for a variety of reasons. So let's talk about the existing Solidity bytecode compiled. So the approach where you compile it, or even transpile, but like compiling gives you the maintainability of the code, is, in my opinion, orders of magnitude faster at the same hardware, at the same proof system than EVM equivalent approach, and happy to be challenged by the.
Okay, very different answers across the board. Jordi, do you want to?
Yeah, I just wanted to give some rough numbers in the prover, the numbers that we are managing currently. Reference machine or reference CPU machine is a single machine with 64 cores. Generating a proof of this 500K gas, the basic proof, we are managing in, let's say, a few minutes. It's 3-4 minutes. That's what we are managing with this approach. At this point, we are also working very hard. We have also these new short fields and optimizations, and a lot of optimizations that we are seeing in the last. And at this point, we don't have like the fine. This can be lowered a lot, but I expect that at the end we can end up easily in a few seconds generating this, which is, well, it's still a lot of hardware power, but something that's much better. When the first proof that we generated, we were in almost an hour, so we having gone down a lot on that. We'll see, but I agree that at the end these are the proving systems, and there is a lot of improvement in hardware acceleration, in FPGA accelerations, in the proof system itself, also in the how you do the design. In the in the internals, we are doing a first approach, but I'm sure that we can have even some tricks to reduce polynomials or to do things better. So there is a lot of margin also for optimization there. So it's a lot of space. I would say that at this point we are in the phase of putting everything together, and then we will see.
So can you share amortized cost per transaction, like on a available hardware on the cloud, for example?
Well, this is the hardware that we are managing is about $2.5, $2.7 per hour.
But how many transactions are in this? But can you just divide?
500K gas in 3-4 minutes.
So like,
need to do that.
So we need to do calculation, but like this is like the order of magnitude is going to be important here. For us, is like roughly 0.1 cent per transaction for like a simple transfer, for example, or Uniswap swap, and this will make a difference for Validium-based systems, where the data availability is not the dominant part anymore, but you want a lot of transactions, like bringing major social networks on blockchain, or bringing just like millions of interactions, like payments and so on and so on, there it will matter a lot.
Right.
And, the comparison point that I would like to see actually is we take Uniswap transactions, we fill a block with Uniswap transactions, and then we see how long it takes to generate the proof. So we can have a very simple comparison with some storage, with some calculations, some hashes, and so on. And we can compare end-to-end, including, for example, verifying the Ethereum signature, all this nasty stuff that we don't always include. And when we will be there, it will be quite easy to say, okay, this is the time for the different rollups. So we take Uniswap, we compile it, and then we see how long it takes to generate the proof. Right. We're not there yet on our end, but hopefully a day will be there.
Like, I also think that all of these proof systems can be parallelizable, right? If you have 10,000 transactions, you'll probably divide it into chunks, and this would get influenced by how well you can parallelize everything. So I'm not sure that like using sequential transaction is the most interesting method.
So you're saying there's a lot of parallelization opportunity, so latency should go down. It's all about cost, really. And maybe to your previous point, these things are going to improve dramatically in the years to come. And we're already on the order of cent or sub-cent, and so maybe we shouldn't be worrying about this. It's going to be negligible cost anyway. Okay, next topic, security. Which one is least liable to having bad bugs? Which approach? Because we've seen bridges, explode. We're going to see rollups explode. Ooh.
It's a tough one, because it's a new technology. There is a lot of new elements that we are introducing from the technology perspective. I already said before that I'm very, at this point I'm focusing the testnet, but testnet to mainnet, just checking everything and being sure that there is that you didn't miss any constraint, that you didn't miss any detail. So it's a big system, and verifying that and putting everything, the effort will be very much like Ethereum itself. It's a system of the complexity of Ethereum somehow. So it's not. It will take time to consolidate, but we need to start. It's a process, but security at the beginning is going to be less
bad.
It's going to be more. It's going to be more risk at the beginning than for when we are 5-10 years running, for sure, like any other system.
Ohad?
Yeah, like I think that security loophole can come from a bug, right? Not from architectural decision. And the only way forward is to roll out very slowly to mainnet, increase the TVL very in a controlled manner, so we can be sure, okay, this system is indeed secure. It's run for like few years. This is the only way to know that something is secure.
Yeah. So when I raised my hand, what I meant is like I was comparing approaches. Obviously, you can make bugs, and obviously, you need to take time for the system to mature and for everyone to gain confidence in it. But let's compare pure approaches, like from left to right. If we start here, we have Transpilation, where you have to maintain the code in a different language, which introduces like an entirely new set of assumptions about the language. Like you will have to re-audit the code, and you will have to think and actually establish new best practices for that language, because they will deviate. Like you will need to maintain the code and develop it further. I think this will take a lot longer to get to the same degree of maturity as we have now on Ethereum, because every best practice we have on Ethereum today is bottle tested and earned by blood and millions of dollars of lost money. And like you go step by step, and you understand, like you have to make those mistakes, you get hacked, get wrecked, then you kind of feel what it means to be secure. So in this regard, theoretically, full EVM equivalence approach could have a leverage, because it should be bytecode compatible with an original code, but you don't get the extensibility to the same extent as you would have on a hybrid approach. That means you will have to go with older means, like for example, building bridges will require the older approaches. Like you will not be able to have like special architecture for native trustless bridges between rollups or between parts of your rollup, which you can implement with those things. So like I think net effect of having this extensibility, having account abstraction rather than relying on the relayers, like native account abstraction built in the protocol, things like this will far offset any like nuances of auditability, and for that matter, with every design decision we make around the compiler is to preserve, like fully preserve the security properties of Ethereum and preserve the auditability of the protocol so that you don't have to re-audit. But one more big aspect of security is like how can you trustlessly enforce your transactions from L1? How do you avoid censorship resistance? And that's where like you need some degree of extensibility to allow something like emergency queues, priority queues from Ethereum to function to its fullest extent.
We're out of time, but thank you so much, guys, for your answers. And